Alright, so our next topic is gaseous equilibria. And a lot of these, you might have noticed, are examples that are gaseous systems. And in some of those cases, it's actually a lot easier to measure pressure than the actual molar concentration of the stuff. Although they are related, they're both a measure of number density. So there is a thing called a pressure-based equilibrium constant. So far, we've only been using molar concentrations, and we call those Kc's. The pressure-based ones you might be surprised to see is called K sub P. And it's constructed the same way. It is in this case, so these P sub C and PD, PA, PB represent the partial pressure of the various reaction components, and as before, the lowercase c, d, a, and b represent the coefficient. And it's constructed the same way. It is the terms with the products on the numerator and the reactants in the denominator, again raised to the power of their coefficient. Now, they're related. And here is, so you should be able to convert from one to the other. So let's just go through this process here. So here's the ideal gas law, talking about, relating the partial pressure of a particular component, in this case A, with the overall volume of the container. Remember, everything here is in the same container, so they share the same volume, or they occupy the same volume. And that's equal to the amount of A in R and T. And again, they're occupying the same volume, and if they're in the same container, you can also assume that they're at the same temperature. Now, the definition of molar concentration is simply the amount of whatever divided by the volume that it occupies, or the volume of the solution in liters. And this rearrangement of the ideal gas law, so Na over V, is going to be equal to the partial pressure of A over RT. Now, let us extend this to an overall equilibrium system. Little a plus little b equals little cc plus little d. The concentration-based equilibrium constant would be this thing that you're getting familiar with now, I hope. Concentration of c to the c power, d to the d power, divided by concentration of a to the a power and b to the b power. Now, let's take this expression, but substitute in these terms with the partial pressure in it for each component. And that would give us this. So we've just got these factors of, each one is now the partial pressure of RC divided by R times T, but raised to the power of that coefficient. Now, because R is a constant and the temperature is common to all components, this can be taken out of this expression, kind of amalgamated and put in front. So this becomes this right here, where now you've got just the partial pressure terms, 1 over RT, and then RT is now to this delta N power. And delta N is merely, so again, depending on the actual values of these coefficients, little a, b, c, and d, that this will be the power of this RT term will vary depending on the reaction stoichiometry. And this delta N is just, you add up the numerator exponents and subtract the denominator exponents. So little c plus little d minus little a minus little b. And this gives us the relationship between, for the same system, the value of Kp and Kc. And the important thing is that they're actually not the same, or usually not the same. So same reaction here is cleared up to give you a little space here. Now, and remember here, this is going to be just, this is what we define Kp as. So we can say that Kc is equal to Kp times this factor of RT to the negative delta N. So if this delta N, if it's positive delta N in the denominator, you can just make that a negative delta N and get rid of that fractional component. Those are mathematically equivalent. And if you want to flip it the other way around, you can say that Kp is equal to Kc times RT to the positive delta N. A couple of other things. For this, you want to use the joules per mole per Kelvin value of R, and not the liter atmosphere mole Kelvin of R. And the one case where, okay, so what makes them equal? So if delta N is 0, anything to the 0th power is 1. So when those coefficients exactly cancel out to 0, then the concentration and pressure-based equilibrium constants are numerically equal. But in general, they're not the same. And here's the big thing. No one ever does this. I have never had reason to convert a Kp to a Kc or the other way around. We just use one and stick with it. And again, since you're generally not the same, just be sure to specify which one that you're using, and you will be fine.